Hey everybody, today we're going to be talking about inverse functions. It's the last day of our function unit. We're going to start with our do now. If f of x equals 2x and g of x equals 1/2 x, we want to find f of g of 2. So hopefully you remember from yesterday's lesson, this notation means I'm going to plug 2 into g first. I'm going to get that answer, and then I'm going to plug it into f. Right? That was composition from yesterday. So f of g of 2 is going to equal 2. Now let's find g of f of 2. Plug 2 into f. And I'm going to take it and I'm going to plug it into g. And I also get 2. So let's just take a second here and look at what happens in each of these cases. So I start with my plug-in number, which is 2. I plug 2 into g, and I get 1. And I plug 1 into f, and I get back to 2. I plug 2 into f, and I get 4, and I plug it into g, and I'm back at 2. Okay. So basically, something we could notice here is sometimes in some situations, the number you plug in under composition is the number you get out. And this has something to do with these two particular functions, okay? These two particular functions are inverses of each other. And when two functions are inverses of each other, this is what's going to happen. All right, so we say the inverse function undoes what a function has done. Okay, now the inverse of a function is defined to be the result of switching the domain and range. Okay, and in our case, we remember domain is really our x's and range is our y's. So it's all about switching x and y here. Just to make a small note right here, an inverse doesn't always have to be a function. We can find the inverse of anything just by switching x and y. In special instances, when the inverse is actually a function, then it's more important to us mathematically. If two functions, f of x and g of x, are inverses of each other, then there are two special composite functions that will equal the same value. Okay, we saw in the do now. So we can say f of g of x equals x, and g of f of x equals x. So whatever we plug in is the number that we're getting out. Now, in order for a function to have an inverse, the original function must be what we call 1-to-1. So basically the easiest way, there's a long mathematical definition, but each x is assigned to only one y, and each y is assigned to only one x. Okay, so it's just a 1-to-1 mapping from one to the other. To determine if a function is 1-to-1, we're going to have two different things we can do. Sometimes you will be asked to just strictly identify 1-to-1 by a set of ordered pairs, in which case x's can't repeat and y's can't repeat. So now it's like going one step more than seeing if something is a function. In a function, each x goes to only one y. But in a one-to-one function, we have to consider each y comes from only one x. The other way, and this is the easier way, this is the method I resort to when I can, by looking at the graph. Now we know when we're dealing with a graph of a function, in order to see if it's a function, we do the vertical line test. We're always going to do that first. Make sure what you're dealing with is a function. And then after that, you do a horizontal line test. So we're going to draw a horizontal line in our graph. And if it intersects more than once, it's not one-to-one. Okay, so same concept. Vertical line test first, then horizontal line test. Let's just, jump into some questions here. In this topic, just identifying is something we need to know how to do. So determine if each function is one-to-one. In case A, I'm looking at a set of ordered pairs. So I'm just going to look to see first my x's. 7, 3, 4, 6. That's good. My x's don't repeat. Now let's look at our y values. 2, 0, 2. Right away, I have a y value repeating. So this is not one-to-one. When I look at a table of values in case B here. Once again, I could go through my x's. -1, 1, 5, 3, 2. Let's go green this time. 6, -2, -1, 2, 3. So nothing repeats. My x's don't repeat and my y's don't repeat. So you could say that this is one-to-one. What does that mean? If we found the inverse of this function, it would be a function as well. That's all. In part C, my vertical line test. So I'm going to do a vertical line test. And as I look, if I go anywhere in this graph, I pass the vertical line test. So now I do the horizontal. And if I look anywhere in this graph, I notice right here, that's a big fail. Okay, so right away, no, this function is not one-to-one. Now x cubed. I don't have the graph in front of me, but we just studied the cubic function. So you guys should be able to, in your head, oh, maybe we didn't. Okay, so I would plug this in my calculator. Sorry, going backwards and forwards at the same time. I would just plug that in the calculator and take a look at it. So if you get this picture, you see passes the vertical line test and passes the horizontal line test. So yes, this function is one-to-one. Now I have the function x squared again. Since I don't have a picture in front of me, I would just visualize it, plug it in the calculator, whatever the case may be. Passes the vertical line test, but does not pass the horizontal line test. So this is a no. However, here's the thing. We can restrict the domain. So this is why when you see some problems in textbooks, they may say, given f of x equals x squared with a restricted domain, x can't equal, or x is greater than or equal to. This is why they do it. So they're setting up so you can answer the particular problem. What does that mean? Well, look, if I just take and look at the section of the graph for the x values, then I'm only seeing this portion of my graph, which is one-to-one. So this is just a special little like add-on explanation of sometimes why you see that. Y equals absolute value of 2x plus 1. I don't care what this picture looks like. All I know is once I see those absolute value signs, I have a V. Okay, that's really what that means. And right away, I can say no. And I'm only being asked to determine, so you're done with the problem. If it can be determined that a function is one-to-one, then the inverse of the function can be found. Now, another note here. We can find the inverse of any function, but whether or not the inverse is a function is what's important to us, okay? So we're going to be dealing with functions that have inverses that are also functions. Fill in the following chart, and this is just going to be a chart to let you know how to do it in different cases if it is established to be a one-to-one function. Notation. Once we find the inverse of a function, that's the notation we use. That -1 is not an exponential rule. It doesn't mean to flip it in this case. When you see a -1 next to a function, or a g, like an f of x or a g of x, that means you're dealing with an inverse function. Okay. And if we need to show, once again, I'm going to go back to the beginning of the lesson. So notice our notation is really, oops. I'm really showing you the same definition. It's just using this more complicated function notation. Basically, different ways. And again, the method is going to be the same in each way with some twists. Okay. Basically, if we want to find the inverse of a numerical, meaning an ordered pair or a table, we're just going to switch x and y. And remember, switching x and y is an easy way of saying switching the domain and the range. Graphical, we switch x and y, and then we graph our new table. And for the analytical, this means when you're asked to write the equation. When we want to come up with an equation for an inverse, we're going to switch x and y, and then we're going to solve for y. And the equation we get will be what we consider our inverse function. Now, things that we focus on in this course, okay, graphing. You may not see the graphs come up on a test or whatever, but it's important to understand the graphing component of this. I want you to be able to identify the domain and range of both f and f inverse and understand the relationship between the two. We want to be able to find the equation of the inverse. If I had to stress something, that would be the most important part of this topic. And we want to show that two functions are inverses of each other. And again, that's more that you understand the relationship. So to start by graphing, I want to graph f and f inverse. So I'm going to set up a table. I'm going to set up my table, x and y. Setting up a table for f. So if I want to graph a line, I just need to pick 3 points. There's no restricted domain to begin with, so I just focus on being in the center of that picture. Plug each of these values into your original function. -2 plus 3 is 1, 3, and 5. -1, 1, 0, 3, 1, 5. I don't have a ruler, very hard to draw on an iPad, but that would be F. Now I want to sketch the inverse. Let's change our color. So when I sketch the inverse, I'm going to go back up to my original table and take each ordered pair and just flip them. 1, -1, 3, 0, 5, 1. Switching x and y. 1, -1, 3, 0, 5, 1. This is my inverse function. It may kind of, let's just make a note of this right now. When we switch x and y, some of you may remember from your geometry class It's like reflecting over the line y equals x. So you can sort of see that reflection. Going back now to our next question, let's identify the domain and range. For this function, it's very easy. They're both lines. So my domain is all reals and my range is all reals. Oh, I might as well write off the word. That's going to be told true for my inverse function as well. Now we want to find the equation of the inverse. So I find the equation of the inverse. First thing I want to do is rewrite and replace f of x with y, because when we're dealing with equations, x's and y's make more sense. Switch x and y. Solve for y. Solve for y means get y by itself. I'm going to subtract 3. So I have 2y equals x minus 3. I'm a big fan of the y value being on the left. Divide by 2. Y equals x minus 3 over 2. Now this really is an equation of a line. It's really the line y equals 1/2 x minus 3/2, which you can sort of see matches our picture. To put this in proper function notation, and I'm gonna use this guy here because it's just easier to work with. That would be our inverse with the proper function notation. And the last thing we're going to do with this particular function is we want to show that they are inverses of each other. So I want to show f inverse of x equals x. And then I want to show f inverse of f of x equals x. Those are two things we need to show. There's f of x. There's f inverse of x. So we're going to just set them up. F of my inverse function, which means I'm substituting the inverse into the function. My 2's cancel. X minus 3 plus 3 equals x. So f of f inverse of x. Oh, I said x and I wrote 3 equals x. Sorry about that. Now f inverse of f of x equals x. F of x is 2x plus 3. So now I'm going to plug 2x plus 3 into my inverse. 2x plus 3, right? That's my plug-in, minus 3 over 2. The 3's are going to cancel out, and we get 2x over 2. And I'm getting mighty squishy, I'm sorry. But ultimately, you see, it winds up being x. So again, that checks out, right? Now, in a particular question, would you be asked to do all of those things? No. I might ask you to do, write the equation in one question. I might ask you to find the domain in another question, all right? But this is what the main topics and concepts that are important in this in these types of problems. On our next example, a little bit of a typo, but I left it a typo on purpose, okay? F of x equals x squared plus 2. Think about this function. It's a parabola shifted up 2 units. So technically, it's really not a one-to-one function. So what was missing from this problem was a restricted domain to begin with. In order for us to deal with this as an inverse, we're going to have to restrict the domain. So now with this restricted domain, we're going to move through our steps. The first thing we want to do is graph it. So if I'm graphing f, I'm going to set up a table. I'm going to pick a couple of numbers bigger than 0. Let's take 0, 1, and 2. I'm going to evaluate them in f of x. 2, 1 squared plus 2 is 3, 2 squared plus 2 is 6. Plot them. And there's your function. While we're here, why don't we, because we have the time, identify the domain and the range since we're doing it anyway. My domain was given to me. And my range, by looking at this picture, is all y values greater than or equal to 2. Now we're going to move on and deal with the inverse. I'm going to set up my inverse table. And again, by just switching the ordered pairs, 2, 0, 3, 1, 6, 2. 2, 0, 3, 1, 4, 5, 6, 2. This is my inverse function. And you can see that reflection in the line y equals x, which is nice when it's obvious on the graph. Now, if I look and I want to identify my domain and my range, I see my domain is x is greater than or equal to 2. And now my range, y is greater than or equal to 0. And it's kind of neat to see here, this relationship between the domain of the original and the range of the inverse. The range of the original and the domain of the inverse, they're completely switched. So it's a nice sort of relationship. Let's find the equation. Y equals x squared plus 2. X equals y squared plus 2. X minus 2 equals y squared. I want to undo that y squared, right? I want to solve for y. So y equals, now technically y equals plus or minus the square root of x minus 2, but as we can clearly see in our graph, we're dealing with the positive version. The negative would make our sideways parabola. So my inverse function is just the positive one, x minus 2. And real quickly, I might just do one show. So I'm going to show f of f inverse of x equals x, right? I'm just going to show that one, even though technically you should show both, but it's just a very repetitive thing. So I'm plugging my inverse. I just want to make sure I see them on my page. I'm plugging my inverse, which is the square root of x minus 2, into my original function. Square root of x minus 2, if I square that, I'm just going to get x minus 2 plus 2 equals x. So that shows that. Okay. You could do it in the opposite order. Again, the next problem involves just doing that, or one of the last problems. So I'm gonna, do that again. So I don't want to waste time on that right now. Now let's look at this. I have f of x equals 2x plus 1 over x minus 1. I want to find g of x, which is going to be the inverse of f of x. So if I want to find the inverse of something, always start by replacing f of x with y. Now we're going to physically switch our x's and y's. Now we're going to do a lot of algebra. Okay. So you're going to have to really be getting, building up your algebra skills here. Think about this. If I want to solve for something, I'm going to cross multiply first. Now I want to get the y by itself, but it's stuck inside parentheses. So I have to distribute to get rid of those parentheses. My goal is to solve for y, so I need to get the y's on the same side. So I'm going to bring this y over, xy minus 2y. At the same time, I'm going to add the x to the other side. Now, since I have a y in each term, right? Now I can factor out the y. And my last step would be dividing through and getting y by itself. This function is our g of x function, right, which is the inverse of f of x. Now, without even looking at the picture, we can find the domain and range of each of these functions. Because what do I know? The domain of the original is the range of the inverse. So looking at my original function and looking at my inverse function, I can answer the next part of this question. The domain of the original, if I'm looking up there, all real numbers, x can equal 1. I can do that in my head. Oops, x. And the range, it's very hard to see what the range is by looking at that. But if I go over to my inverse, I can get the range there. Or I could just jump over here and do the domain. It's a little bit easier to do it this way. X can't equal 2. So the range becomes all real numbers. Y can't equal 2, right? And the range becomes all real numbers. X can't equal 1. They just sort of switch. Okay. F of x and g of x. This happens when they're inverses of each other. Let's look at one more example here. Determine if the pair of functions below are inverses of each other and show your work. Oh, this is actually the example from above, but it doesn't matter. Okay. To show they're inverses of each other, we want to show that f of g of x equals x. Then we want to show that g of f of x equals x. I could change numbers, but it doesn't really matter. We're going to plug g of x into f of x. Right, so that's that side. And then we'll do g of f of x. And that's that side. So yes, f of x and g of x are inverses. Okay, thank you guys, and we'll see each other soon.